Welcome back. This is the second episode in a series of videos where I disassemble the American Girl pinball machine. In the previous video, I disassembled the machine mechanically and started doing some circuit analysis on the PCB in the back box. In this video, I'm going to tackle the larger PCB in the playfield. I've been following the traces on the main PCB using a program called Visio. I take a picture of the PCB, blow it up, and then use this program to make connections like this on the traces. It helps me visualize where the traces go. I'm in the middle of following the traces for the optical sensors. You can see there's 3 sensors on the board. You can see I've got this one traced out and that one traced out. There's one left down here in the ball trough. So I'll show you how I trace that one. The last sensor that I have to trace is down here in the ball trough. It's these 4 pads here. In an optical sensor like this, there's a sender and a receiver. I'm not sure which of these is the sender and which is the receiver, but let's pretend this one's the sender. So the sender sends an infrared beam across to the receiver. When something crosses that path, like the pinball in this case, it breaks the beam. At that point, the receiver sends a signal back to the microcontroller to let it know that something has broken its beam. So it acts like a switch that is activated when something crosses the beam. So I need to follow these pads and figure out where they go, which will let me know which of these is the sender, which is the receiver, and also trace them back to the microcontroller so I know which of these pins enables the sensor and which of the pins is triggered when something crosses the path. So I've got Visio running up here. I've already traced power through the board to both of the parts of the sensor. One of these is the sender and one of them is the receiver. They're both getting power. Now I need to figure out where this trace goes and where this trace goes. So all I do is visually follow them. It's much easier to do it here in Visio than it is to do it looking at the board. I can see this trace passes through a pad on a resistor, but it doesn't actually need to cross the resistor to make its connection. So I'm going to keep going. It gets very small. I'm not sure where that one goes. I need to zoom in. It's much easier to zoom in and see where things go. The board is kind of dirty. The backbox board was pretty clean. The playfield board is pretty dirty. So it looks like it crosses underneath this jumper. When I first saw all these jumpers on the board, I thought they were maybe testing or diagnostic, or maybe different configurations the circuit can be in, because I'm used to jumpers being able to be populated or not be populated and change the behavior of the circuit. But in this case, I think they're just using these jumpers to cross traces. So this trace between here and here has to cross these traces that go this way. Normally you would do like a dual layer board to do that, where you've got circuits printed on the top of the board and on the bottom of the board. But it saves cost to do a single layer board. So they've chosen to do a single layer board and use jumpers to cross the traces. It must have saved them a few bucks. So this trace goes underneath the jumper and goes up to the microcontroller and then disappears. So this is where it gets interesting, because this trace is going underneath the microcontroller board, and it's probably ending up on one of these pins, but I'm not sure which one. So I need to use the multimeter in continuity mode to figure out where that trace goes. So I need to find the last component at this place, the last component that the trace touched, and measure from there. It didn't touch that jumper. It did touch this resistor, but the trace keeps on going. So I can actually measure from right where the sensor started. So let's do that. We're looking at the rightmost bottom sensor pad. And then I'm just going to assume that this trace goes straight to one of these pins. So let's test that assumption. So meter in continuity mode. It is the bottom right pad of the sensor. It disappears onto the board somewhere around here, so let's just try each of these pins on this side because it's closest. Oh, there it is. Okay, so we're looking at the first, second, third, fourth pin from the bottom right. Alright, fourth pin, 1, 2, 3, fourth, that's pin 12. So I can extend this line now and take it to pin 12. I've been keeping a little spreadsheet of each of the pins on the micro. And what it controls. So now I know that pin 12 goes to the sensor that's labeled as sensor 14. I don't know yet whether that's the sender or the receiver. I'll have to look at the circuit more to figure out. Let's take a look at these other pads. So I've got this one pretty much mapped out. It's just getting power to one side of the LED, and then that LED is being grounded on pin 12. This one goes through some components, so let's take a look at that. Looks like it hits, what is that, R23? And then it looks like this trace continues to this resistor and across to that pin that goes to the microcontroller. I'm going to follow it this way. It goes underneath jumper 7. Up to jumper 13. And then crosses underneath jumper 6. And up to pin 16 on the microcontroller. And I don't want to forget about this area down here where it crossed over to the other microcontroller pin. There, so we can see now that I've got all 4 of the pads traced out, and they're being that sensor is being controlled and monitored by pin 12 and pin 16 on the microcontroller. So we've got sensor 14 on 12 and 16. That was the last of the sensors that I had to map out, so now I have all of them. And I can start to get an idea of how they work in the circuit. Power for all of them is this red circuit here, and it goes through a small transistor, Q6, here, which is controlled by that orange trace, BP6, from the backbox. So it looks like the backbox can enable and disable all of the sensors on the board by controlling their voltage, their positive voltage. I'm not really familiar with optical sensor wiring, so I've had to look it up to see how it works. Let's take a look at sensor 1 here. Both sides of the sensor are getting positive voltage. So it looks like the grounds are going to the microcontroller, this dark blue line and this light blue line. I'm not really sure which of these is the sender and which is the receiver. But from reading up on it, the way it works is the sender is always conducting. It's always sending a beam of light across. The receiver, when it's sensing that light, will conduct. And when it stops sensing the light, it won't conduct. Power from both of these has to pass through some kind of current limiting resistor. Otherwise, you damage these components and probably damage the microcontroller that's providing a ground. So, since both of these have to pass through a resistor to get to ground, I think that the ground is this trace here, because power comes in through here, goes across the resistor to ground, power comes in here, goes across the resistor to ground. So I think pin 3 on the micro is providing a ground. That leaves pin 4 sensing whether one of these is still conducting or not. So I was taking a look at this description of how to use an optical sensor with an Arduino, and this circuit is useful. So there's the sender here. When it has power, it sends infrared, it emits infrared. The receiver here, when it's seeing the infrared beam, it will conduct. When it doesn't see the beam, it will stop conducting. But it's useful to me to see that the sender has a resistor that's a low value, just a current limiter resistor on the emitter, and the resistor on the receiver is a higher value. So I can check these two resistors here and see if one is low and one is high. Put my meter in resistance mode. The two resistors are right here, so we'll do the one on top. 220 ohms. The one on bottom, 10k ohms. So 220, 10k. The path to ground for this part of the opto goes through 220 and straight to here. So that makes me think that this one is the sender. This one being 10k makes me think that this is the receiver. So I think my theory is right, that this dark blue line is the pin that detects whether the receiver is conducting or not. So back to my spreadsheet of connections. I can label pin 3 as maybe the enable pin for sensor 1 because it provides the path to ground for both of them, both the sender and the receiver. Then I can label pin 4 as maybe the sensor pin. That can tell if the beam between the sender and the receiver is broken or not. Maybe sense. I think this pin will see high if this is conducting, so if the beam isn't broken, and it will see low if this is not conducting and the beam is broken.
I followed nearly all the traces on both the playfield board and the backbox. My goal in doing that is to see what functionality is available on both of these boards. For instance, which switches I have access to, which LEDs can be controlled independently, how the different LEDs are controlled, how things play together between this board and the backbox board. And most importantly, how this microcontroller works, or at least how its external inputs and outputs work, what each of these 30 pins does. My end goal being to replace this microcontroller with my own. Let's walk through each of the two boards and get an idea of what capabilities each has. The board in the back box controls 6 different LEDs on the playfield, that's these purple lines, and also controls 3 different LEDs in the back box. For the 6 LEDs in the playfield, the traces go straight from this N55P controller to the playfield. So there's not much interesting here. For the 3 LEDs that it controls in the back box, one of them is controlled independently. I called that one LED X. That is the LED at the top left of the back box. The other 2 LEDs in the back box are controlled together. So this controller can turn them on and off, but it controls both of them simultaneously. Those are the 2 LEDs that you see at the bottom of the back box. They're controlled through this transistor here. Also in the back box is this kind of mysterious BPC6 connection that goes straight from the controller to the playfield. We'll talk about that later. One of the most important things in the back box is this SPI connection. So it's a 3-wire protocol. If you look at the 3 pins, we've got CSB, SCK, and MOSI. MOSI stands for Master Out Slave In. So in this case, the controller on the playfield is the master, and it's talking over this line to the slave, this N55P LED controller. The other 2 pins, the chip select, if you've got multiple slaves, the master can control which slave it's talking to by raising or lowering values on this line. In this case, there's only one slave. So this line, I think, is always kept low. The third one is the clock. So that's how the master on the playfield clocks data in to this chip. The SPI bus is presumably used to control the 6 LEDs in the playfield and the 3 LEDs in the back box, and also the score digits. So all this circuitry that you see here is used to manipulate the 6 digits on the score display. The only interface between the main microcontroller and the playfield and this subcontroller in the back box is this SPI interface. So anything that this chip controls is probably going to come over this bus. So when I take a look at the data on this bus later, I'm expecting to see a way for the main microcontroller to control the 6 score digits and all 9 of the LEDs, or 8 independently addressable LEDs, through this controller. So the SPI bus goes in between this slave controller in the back box, through these traces, down to the main microcontroller on the playfield. So you see those same 3 lines, the CSB, SCK, and MOSI, going straight from the ribbon cable from the back box through to pins on the microcontroller. I've never messed with an SPI bus before, so I was happy to see that there's no other circuitry in line with those pins. It just goes straight from the back box to the micro. So I should be able to just tap into the pins here and see what data is coming across that bus. With any luck, I'll be able to decipher the commands that the micro is sending to the controller in the back box, and maybe be able to control it myself with a different microcontroller. I should be able, just by connecting to these traces on the back box, I should be able to control the score digits and all of these LEDs from my own microcontroller. But before we get to that, let's keep walking through all the traces on the playfield board to get an idea of what else we could control if I replaced that microcontroller with my own. There are a number of LEDs that are all controlled between the main microcontroller and the slave and the backbox. The traces here on the playfield for the LEDs are kind of hard to follow because of the power wire. They are all powered from VCC, this red line, and most of them sync into the main microcontroller here. Let me take the red line off. It'll be easier to see what's going on. There. So we've got 6 LEDs that are controlled from the back box, following these traces here. And then 6 LEDs that are controlled straight from the microcontroller. Don't worry about these lines that go through the microcontroller. They're actually going under it. Some of them go in between the pads of the micro. But look at the ones that go straight to a pad. Those are controlled by the microcontroller here. There is, oh, and this one down here too. There is one interesting thing that I found. So pin 30 of the microcontroller is this blue line here. It's controlling LED H and LED F. That's here and here. But it's unlike the other LEDs. All the rest of the LEDs in the playfield, they get power from VCC, and then the microcontroller syncs, provides ground for those LEDs. But the 2 off of pin 30 don't. So this line here turns on or off this transistor, and then gives these 2 LEDs power, and that power is synced straight to ground. So these 2 are different, and they're not controlled independently. They're controlled as a pair. I kind of think that maybe they ran out of pins on the microcontroller between the micro and the backbox controller, because almost all the LEDs are controlled independently except for this pair that are the top 2 pops, and then the other pair in the backbox. There are 3 optical switches on the playfield, and each of those switches has 2 pins on the microcontroller. I've called them the enable pin and the sense pin. So for instance, sensor 14, that's this one down here in the ball trough, senses when a ball is lost. That sensor has its enable pin on pin 16 of the microcontroller, and its sense pin on 12. I'm not entirely sure what's going on here. My theory is that both the send and receive side of each of these switches is always or almost always getting power, and the microcontroller is providing a ground for the send side. So the microcontroller can control whether the send side here is on or off. Then it uses this sense line here to tell when the beam has been broken, so when a ball has passed through it. I say that they're almost always getting power because I think this power is actually controlled by the controller in the back box. So it's all of the power from all three of the sensors is coming from this line here that comes out of this small transistor. And it looks like that BP6 connection that we saw earlier in the back box is turning this transistor on or off. But if that's the case, I don't know why the sender needs to be turned on and off by the microcontroller. Because the micro could just tell the back box to turn it on and off. So I'm not really sure what's going on there. But I do know that the microcontroller has 2 pins for each sensor. Along with the 3 optical switches on the playfield, there are also 7 physical switches. 3 pops, 2 stand-ups, and 2 slings. All of those switches attach to the microcontroller through this 5-pin connection down here. So there's a ground across 2 different pins, and then there's only 3 pins left. So although we have 7 switches on the board, we don't have 7 independently visible switches. There's one connection to the microcontroller for the 2 slings, so you can tell when either of those slings has been hit, but you can't tell which one was hit. There's another connection for the 2 stand-ups. It's the same way. You can't tell which one was hit, but you can tell when they were hit. And another connection for all 3 pops. So you can't tell which pop was hit, but you can tell that a pop was hit. The final switch that the microcontroller listens for is the start button. That comes through on pin 18 of the micro. Next to the microcontroller is another small IC. I had to get a camera pretty close to figure out what that actually is. It's an EEPROM. So there are 2 different connections on the microcontroller for that EEPROM. I'm not really familiar with how EEPROMs work, but these 2 pins control it, this SDA pin and SCL pin on pin 26 and pin 25 of the micro. I think the only thing that it's storing in this EEPROM is the high score. The reset pin for the microcontroller is in that same area. It's just coupled to ground with a capacitor up here. The microcontroller is directly attached to the speaker. There's no other audio processing chip. It just uses PWM or pulse width modulation from the microcontroller to actuate the speaker. The interesting thing here is the positive voltage goes directly to the speaker, and the negative voltage goes through 1 or 2 resistors, depending on the volume switch. So if the volume switch is set to low, then the negative pulse width modulation has to travel through 2 resistors, a 33 ohm resistor and a 150 ohm resistor in series to get to the speaker. If the switch is set to high, then the path is shorter, and it only has to go through a 33 ohm resistor. It bypasses the 150 ohm resistor. So it makes the speaker louder. That's how the high-low volume switch works. So what's interesting to note here is this microcontroller is able to produce sound just with its PWM chips. So if I replace this microcontroller, I need one that can produce its own sounds. The micro also appears to have control over the motor. So when you're playing the game, that motor is always on as long as the game is started. It's not turned on or off during the game, but it looks like it could be. The motor is powered off the battery directly. It doesn't go through any kind of regulator, but it does pass through a transistor that seems to control whether it has a path to ground. That's controlled by pin 7 on the microcontroller. So it looks like we could turn the motor on and off during gameplay. So the motor is powered off the battery, but nothing else is. All the rest of the power goes through a voltage regulator down here. I'm not really familiar with with power circuitry, but it looks like this positive voltage comes in from the battery, goes into this regulator, and then that's about 4.5 volts. It's 3 C batteries at 1.5 volts apiece. And when I measured the voltage coming off this regulator and the voltage at this VCC pin here on the microcontroller, it was 3.5. So maybe this is a 3.3 volt microcontroller, and they're just running it at 3.5. But anyway, the power is regulated by this chip here. What I find really interesting, and it's still kind of a mystery to me, is what this is doing. So this is the VCC pin on the microcontroller. This is the ground pin. You'd expect to see both of these, but this third pin here, I'm not really sure. When I measure what comes off here, I see 3.5 volts. This chip here, I'm not really sure what it is, and I can't find any information about it online. My guess, like I said, I'm not really familiar with power circuitry, but my guess is it's a FET, and maybe it's acting as a low voltage protection. Maybe if the voltage coming off of this pin, this pin seems to always be enabled during gameplay. Maybe if the voltage coming off this pin drops below acceptable levels, then this starts conducting. And if it does start conducting, then the power coming from the battery maybe gets shorted back to the negative battery terminal, bypassing this voltage regulator and shutting down the microcontroller, and actually shutting down everything, because nothing gets power then. Even the motor, since it's controlled through this transistor. So that's my going theory. Maybe they were afraid the battery voltage might drop below acceptable levels, and things might get wonky. The microcontroller might start misbehaving. I don't know. That's my going theory, that it's some kind of protection against low voltage. I think that's something I'll just have to explore if I ever replace this microcontroller with my own. So putting it all together, I get a pretty good idea of everything that's connected to this microcontroller and all the different capabilities that it has. So we've got LEDs being controlled by pins in yellow, switches and sensors on the playfield being controlled by this bluish color pins, the 2 speaker connections, the ability to turn on and off the motor, some kind of mysterious low voltage protection maybe, and EEPROM in purple here to store the high score, a connection to the back box that controls the score digits and some of the LEDs. And putting all that together, I think we've got a pretty capable playfield. There's several different independently controllable LEDs. I expected a lot of these to be tied together, but there's only 2 pairs that are tied together. So we could have a pretty good light show, I think. A lot better than what's in the machine now, since all of these LEDs are independently controllable. And in terms of the switches, it was kind of what I expected. Lots of these switches are tied together, so like I said before, the slings here, you can't tell which one was hit, but you can just tell that one of them was hit. It's the same thing with these stand-ups. It's the same thing with these pops. But it is still pretty cool that you can tell when a ball has been lost, because you can tell when this beam has been broken, and you can tell when a ball has been plunged, because this beam is broken. So you could have a ball counter, for instance. That's something that the machine does now, but it doesn't give you a display for it. So I'm really looking forward to kind of hacking that SPI connection between the playfield and the backbox, and see what can be done with these 6 digits here, and how those are controlled. Because maybe I can throw up some alphanumeric stuff up here to give a visible ball counter. And maybe with all these different LEDs that I've got control over, maybe I can throw up some alphanumerics that have different modes and different things to shoot for.
I really wasn't expecting all these LEDs to be independently addressable like that, because the software in the machine from the factory seems to have all of them turned on at once, and maybe flash these, and maybe flash these right here, but not do any kind of intricate light show that they could do, because they're all controlled independently. I'm pretty excited that there might be more capability in this machine than what the factory software uses. But to unlock any of that capability, I'm going to have to figure out the protocol that's used to communicate from the microcontroller to this controller here in the back box. So I'll have to tap into the SPI pins here and see if I can get any information from them and decode it and try to make some sense out of it. To do that, I'll have to get this board powered up outside of the machine. So in the next video, we'll tackle getting this board powered up using a bench power supply and taking a look at this SPI interface to see what data comes across it and see if we can make any sense out of it. See you then.